So, welcome everyone to the second session of for today, second and last. And we welcome Stephan Wagner from Technical University Graz and Uppsala University. And he will talk about tree enumeration and tree statistics. Stephan, please.
Very much for the introduction, and thanks to the organizers for inviting me to talk at this conference. It's a great opportunity for me to talk about one of my most favorite topics, which is trees. So mainly this talk will be a lengthy commercial break where I'm trying to sell various types of trees to you. So I will be introducing various different families of trees and the resulting combinatorial enumeration problems. To give you a bit of an idea of how rich and wide this field is, actually, I'm constantly amazed by how many different types of trees there are and how many interesting counting problems you can find by just looking at trees. So I've already given away the first slide almost accidentally, but I'm sure I'm not the only one here in this audience who enjoys the XKCD comics. So I found it quite fortuitous when yesterday this comic here appeared there, showing the three kinds of scientific research. And my talk will be of this third type, where I'm trying to produce a map of every kind of tree available, which is difficult, and I'm certainly not going to succeed. But I would like to cover as many possible types of trees as I can think of. At the beginning, there will be some classical families of trees and some very classical enumeration results about these. So it's quite likely that many of you will know all of these already. Towards the end, I will give you three examples of somewhat more unusual types of trees that occurred in my own work over the years, which people might be less familiar with. So, as I said, there are many classical types of trees, classical families that people have studied and enumerated. You can, of course, consider labeled trees. Plain trees is another type that comes to mind. All of these will be shown later on with examples, of course. Binary trees, polytrees, non-crossing trees, recursive trees, binary increasing trees. So all of these will feature in the following. I'll give examples and some related results about all of these. And as I said, later on, I'll talk about some more unusual types of trees. Right, so what are all of these? Labeled trees, for a start, are maybe in a way the most natural. You take vertices labeled with the numbers 1 to n, and you build a tree from these. These trees can be rooted or unrooted, but otherwise only edges between vertices matters. So the order of children, for example, is irrelevant. I could put the 4, 7, 10 here in a different order, would still be considered the same tree. Each vertex has a unique label, so the labels are the numbers from 1 up to n. And of course, it's a well-known and classical result due to Cayley that the number of unrooted labeled trees is n to the n minus 2, whereas the number of rooted labeled trees, where in addition you distinguish one vertex called the root, let's say vertex number 5 in this example, is just n times that, because you can pick any of your n vertices as the root, so you get n to the n minus 1. Plain trees are similar yet different. So these are also rooted trees. These are ordered trees, so I do care about the order of children or the order of branches. So I would not be allowed to permute the 3 trees over 3 branches over here. It would give me a different tree. And of course, it's a well-known and classical result that this is one of the instances of a combinatorial object that gives you the Catalan numbers. There are very many more. This is one of the more classical and well-known ones. Another one that also yields the Catalan numbers are binary trees. Here, there are two versions that you can consider. If you consider some full binary trees where each vertex has exactly two children, you obtain the whole tree over here, both including the blue and the red vertices. So here, every internal vertex, every non-leaf, it's all those vertices marked blue, have exactly two children. And if you remove all the leaves, then you're left with a type of tree that's called pruned binary trees, where each vertex can either have two children, a left and a right one, or just the left child, or just the right child, or no children at all, in which case it's a leaf. So the number of binary trees within internal vertices is also a Catalan number, of course, and this formula generalizes to d-ary trees, where just here in the denominator, you have a slight change, and two changes, generally to d. All right, so far so classical. All of these three are instances of what one calls simply generated families of trees. So Mir and Moon in the 1970s wrote a series of papers studying these trees at length, and there has been a lot of literature later on these so-called simply generated families. One way of defining them maybe is to say that these are families that have generating functions satisfying a specific type of functional equation, namely this one here. So t, the generating function, is x times some function phi of p of x. And this is just a sort of representation of the way trees are constructed. The x stands for the root, and the phi of t of x for the collection of branches you get. And depending on how you count them, you need different functions phi there. So e to the t gives you rooted label trees that we've had. 1 over 1 minus t gives you plain trees. 1 plus t squared gives you binary trees. And 1 plus t bracket squared gives you pruned binary trees. So you see that each term t to the k basically stands for a root with k children. So in 1 plus 2t squared, you would either have no children at all, that's the one, or 1 with 2, or a root with 2 children, which the t squared stands for. Here, if you multiply out, you get 1 single root, or 2 ways to get a root and a single child, or a root with 2 children. All right. All of these have very similar properties. One of these properties is that the coefficients of the generating function satisfy an asymptotic formula that looks like this. For certain constants a and b, the coefficient tn in t of x, which is basically the number of trees. I'm saying basically because it isn't always. If you study rooted label trees, for example, t is actually an exponential generating function, and this is only true up to factor n factorial. But generally speaking, under reasonably mild conditions on theta, on phi here, you have this type of asymptotic formula, which comes from a square root singularity in the generating function t. Linear trees are my next example. They're a bit similar to simply generated trees. In fact, not just a bit, they're very similar. So these are rooted trees where the order of children suddenly doesn't matter. So if I were to permute the 3 branches attached here, so this one, this one, this one, it would still count as the same tree, unlike the plain trees that we had earlier. If I were to switch this branch and this branch here, I would still be getting the same tree. So here we're basically counting trees up to isomorphism, either rooted trees, or one can also look at unrooted trees. So these are, as I said, not quite simply generated. They satisfy a rather similar type of functional equation, except that the right side of the equation isn't quite of the form phi of t of x, but it is something a bit more complicated. It involves the function t, but in a somewhat more complicated way. So specifically, you're getting t also evaluated at powers of x. Nonetheless, there is an asymptotic formula of the same kind, a and b being constants. These are also sometimes referred to as Otto's tree enumeration constants, because this was proven in a paper by Otto, I think 1947. So not just this is one of the similarities to simply generated trees, but also many structural properties are quite similar. So I'll talk about tree statistics and structure a bit later. So in that regard, polytrees are quite often very, very similar to all the simply generated families, even though they are not quite simply generated themselves. If you take the family of unrooted, unlabeled trees, where simply you ignore the root, and there is also no order among the neighbors, you're just counting unlabeled trees up to isomorphism. That's a closely related family, and in fact, you have very similar asymptotic formula, except that here the exponent changes to 5/2 instead of 3/2, and there is a slightly different constant a prime here instead of a. But the b is the same, so the exponential growth is the same for both. So non-crossing trees are perhaps already a bit more specific. I would still consider them classical there, but they're perhaps already less well known. So these are trees where you arrange the vertices on a circle. So here I have a non-crossing tree with vertices 1 to 12, and the edges are not allowed to cross. So I would not be allowed to have, say, an edge between 9 and 12 here instead of the edge between 9 and 10. Or edge between 10 and 12 instead of the edge between 9 and 10. That would still give me a tree, but it would no longer be non-crossing because I would have two intersecting edges. Now, there's a nice counting formula for these non-crossing trees as well. Number of non-crossing trees within vertices is 1/2 n minus 1 times 3 n minus 3 choose n minus 1, which also is the same as the number of ternary trees with n minus 1 vertices. And indeed, you can construct bijections between the two. So there is, for example, a very nice paper by Panholz and Proding about this. Non-crossing trees are also not quite simply generated, but they also do share many of the same properties. So in terms of structural things, one can relate them. One of the things, for example, is that the generating function has the same kind of singularity, and therefore, if you were to take asymptotics of this quantity, you would get something similar. Right. Let's move on to my next example. You see there are quite a number. Recursive trees can be constructed in different ways. One of them is by a recursive procedure where you add vertices step by step. So you start with a vertex labeled 1, vertex labeled 2, 3, 4, and so forth. And you keep doing that. So each step you attach the new vertex to one of the all the vertices that are already present. So keep doing that. So here now I have a recursive tree with 10 vertices. You see that naturally, due to the way it's constructed, the labels always have to increase from the root to the leaves. And it's clear from the construction that there are precisely n minus 1 factorial recursive trees with n vertices, because in the nth step you have n minus 1 choices. Your nth vertex can attach to any of the previous n minus 1. So it's just taking the product of that, giving you n minus 1 factorial. So this suggests connections to permutations, and indeed there are some very nice, very classical ones, which I will also explain in a moment. A similar type of trees is what is called binary increasing tree. These are constructed in a similar fashion, except that new vertices can either be attached as left children or as right children. So I'm doing the exact same thing, following the same procedure, except that each time I'm attaching a vertex, it can either go to the left of one of the previous vertices or to the right. So here, for example, the new vertex 2 goes to the left of vertex 1, 3 goes to the left of vertex 2, and 4, something went wrong there, my mistake. So 4, 5, 6, 7, 8, 9, 10. And you see that, again, the number of ways you can attach your new vertex is deterministic, and it's rather simple. At the beginning, you have 2 possible places where you can attach. Once you attach a vertex, one of the places disappears. You can no longer attach here, but 2 new places appear. So when the vertex number 2 was attached here, 2 new possibilities opened up for a vertex to be attached. So now you have 3 possible places where you can attach, and then in the next step you have 4, 5, 6, and so on. And so there are precisely n-factorial binary increasing trees within vertices. These are 2 examples of what one calls simple varieties of increasing trees. These families are, among other things, characterized by having exponential generating functions that satisfy this particular kind of differential equation. And you see it's very similar to the definition of simply generated families. That's no coincidence. The T prime here basically means sort of assigning label 1 to the root, and then phi, again, plays the same role as it did before in the context of simply generated families. So if you take phi to be e to the t, then you get recursive trees. If you take phi to be 1 plus t bracket squared, then you get binary increasing trees. Other examples that are nice and classical are plane-oriented recursive trees, also abbreviated to ports, where phi is this function. These are counted by the double factorials. And another nice example that I like are binary increasing trees with an additional full, where vertices either have 0 or 2 children. So that means 5t would have to be 1 plus t squared. And if you then solve the differential equation, you find that t is precisely the tangent function. So these increasing trees, where each vertex has either 2 children or none, are counted by the tangent numbers, which are the coefficients in the expansion of the tangent function, up to, of course, the denominator of n factorial. Right, so all of these are varieties of increasing trees in that the labels have to increase from the root to the leaves. So that's the connecting feature there. Both with simply generated families and with these increasing varieties, there is also a probabilistic side to them. The notion of simply generated family of tree is in a way equivalent to the construction of Galton-Watson trees, conditioned Galton-Watson trees, perhaps to be more precise. Whereas many of these simple varieties of increasing trees can be constructed from a recursive procedure like the recursive trees and the binary increasing trees. Binary case generalizes to a D-array type of trees, and these plane-oriented recursive trees are an example of what you get by some kind of preferential attachment algorithm. All right, let me now move on to tree statistics, and this is by no means supposed to be an exhaustive list of anything. It is a few examples that I find nice and pretty of enumerative results about various types of tree statistics, just to give an idea of what kind of features, what kind of statistics associated with trees one can study, and what kind of results one can perhaps expect around these. Maybe one of the most natural and classical are degrees. So you count not just how many trees there are, but how many trees are there with some sort of degree condition. So one way of generalizing Cayley's formula, this is also quite classical, is that this polynomial here is the multivariate generating function for vertex degrees. What this means is that if you multiply this whole thing out and take the coefficient of some monomial, then it is exactly the number of labeled trees where the degrees correspond to the exponents in that monomial. So vertex k has degree ak for every k. Right, so this is some sort of folklore result, but one can actually go even further. So we can add even more variables and refine this a bit further. If you count labeled trees with the additional restriction that vertex k has a certain number of edges going to vertices of higher label and a certain number of edges going to vertices of lower label, then you get this polynomial when you multiply it out. So you have twice as many variables as you had here. If you set yk equal to xk in here for all k, then it's not difficult to show that what you're getting is exactly this. So it specializes down to that one. And if you specialize further, if you make all the x's equal to 1, then of course you're getting Cayley's formula back. So then this product is 1, and here this sum is n, so you get n to the n minus 2. So it's quite nice that you can include all these features and still get something very, very compact and explicit in this polynomial here. Another example, and this one is quite famous, is that the number of leaves in plane trees is one of many ways to get the Narayana numbers. So the number of plane trees where you have n vertices, k of which are leaves, is precisely this quantity, which is a Narayana number. To illustrate this, just to give you an example, here are all the plane trees with 5 vertices, and I've grouped them according to the number of leaves. So we have one with 3 leaves, then there are 3 with 2 leaves, and only one with 1 leaf. And these are exactly what you get if you plug n equal to 4 in here, as well as k equal to 3 to 1. You should be getting these Narayana numbers there. Now, I mentioned earlier that there are connections to permutations. As you would expect, if something is counted by the factorials, and that's the case both for recursive trees and for binary increasing trees. So they're in bijection with permutations, and for many statistics associated with permutations, you have a counterpart in the tree world and vice versa. So for some interesting statistics of trees, you have an associated a statistic in the world of permutations. To give you an example of this, the number of recursive trees where you have n vertices and the root degree, the number of children of the root is exactly k, is precisely the Stirling number. This is a well-known interpretation of the Stirling numbers here. The number of binary increasing trees is n factorial, but again, you can refine them adding additional statistics. So here, just for the sake of the example, I've taken the number of left edges. So that's the number of edges going to the left. If you take that, you get the number of permutations with k descents, which is called an Eulerian number. Right, so the number of left edges corresponds to the number of descents. The descent in a permutation, of course, we've had that already today, 2 consecutive elements of the permutation where the first one is greater than the second. All right, so classical permutation statistics correspond to things in trees and the other way around. And these are just 2 examples. This is, again, by no means an exhaustive list. Right. So something related, since I was just talking about descents, you can also define descents in labeled trees, and these have been studied too. So recently I was working on something where this became important. Descents in labeled trees are pairs of adjacent vertices where the parent has a greater label than the child. So you're going down from the parent to the child. And as it turns out, you can count trees with respect to the number of descents, and the result is very nice. So again, you have a polynomial that counts labeled trees by descents, in the sense that if you multiply this whole thing out here, then the coefficient of q to the k is precisely the number of rooted labeled trees with n vertices and k descents. So two of the formulas that I've shown you today can be obtained as simple specializations of that, because if you take q equal to 0, it means that you're simply not allowing descents. Then this disappears and you're getting n minus 1 factorial, which is, of course, recursive trees. Recursive trees, by definition, do not have descents. On the other hand, if you make q equal to 1, then the j's here cancel, you get n to the n minus 1, and you've got rooted labeled trees, because you're basically losing the information on descents altogether into counting all of them equally. So we've had several examples where a tree statistic gave rise to some nice explicit enumerative formula. This is, of course, in a way, the best thing you can hope for. You're interested in the distribution of some kind of tree statistic, and you have a formula that's completely explicit, or you have some nice polynomial, as in this example, that's given explicitly and acts as kind of a generating function for the statistic you're interested in. But of course, things are not always that simple. And a good example to illustrate this is coming now. So often asymptotic results and things about the limiting distribution are, in some sense, the best you can hope for, in general, at least. So a good example is the height. Height is a very natural tree parameter, also relevant in various different contexts. So it has been studied quite extensively, of course. It's the greatest distance from the root to a leaf. So it is known that for simply generated families of trees, again, some mild conditions need to be assumed, the height is of the order of magnitude square root n. So if you have a large simply generated tree, then so on average, the height is going to be of the order of magnitude square root n. And if you look at the distribution and scale it, so if you divide by square root n, then up to some constant, you have convergence in distribution to something that's called a theta distribution. The theta distribution can be characterized in several different ways, one of them being by the cumulative distribution function given here. So this general version for simply generated families of trees is due to Flageolet-Gao, Oblisco, and Richmond, who showed this convergence to theta distribution. You can say quite a number of things about this theta distribution. It's quite unusual looking. If you look at it initially, then, for example, it's not at all clear immediately that this would really represent a distribution function satisfying all the properties that a distribution function should have. But it does. It's equally not clear that these two things really represent the same thing. It's a rather non-trivial identity between theta series. But you can say quite a number of things about them, moments and so forth have all been studied. So this is a good example where you have some result about asymptotic behavior or limiting behavior of sorts. All right, so now I'm moving on to the types of trees that I think most of the people in the audience will not be that familiar with. One example I will give is canonical trees. Another example is increasing trees with label repetitions. I will define what exactly that means. And the last one will be a kind of curious example of something that we call K-plane trees, which in a way are a generalization of plane trees. So these are types of trees that I encountered over the years and which have some curious and maybe unusual properties. So the first type I want to talk about is from the family of canonical trees, as we dub them. They're related to, among other things, partitions of 1 into powers of an integer. It doesn't have to be 2, but I'm using 2 now in my example. So I'm looking at ways to write the number 1 as a partition into powers of 2. To make this meaningful, the exponent should be negative. Or if there is only one of them, I might allow 0. So the a's here are integers. Without loss of generality, I'm not caring about the order. I put them in increasing order. So these partitions are related to prefix-free codes, and that was one of the ways these representations were approached. So prefix-free code is a set of words, thinking of them as 0-1 strings now, such that none of them is a prefix of the other. So none of these strings occurs at the beginning of another one. Then there is an inequality that says the lengths of these have to satisfy certain inequalities called Kraft-McMillan inequality. This bounds the lengths of these code words or strings. Now, if this holds with equality, we're exactly back to the original equation here. The codes that satisfy this with equality are called compact, and they're in some sense optimal in an information theoretical sense. So you cannot have more information in a prefix code than in a compact code, basically. Right, so now one might wonder how many possible solutions there are to this kind of equation. And this is equivalent basically to how many such codes there are up to a certain kind of isomorphism. So we would like to count the number of solutions to this. Now, you don't see any trees yet, but they will appear in a moment. It turns out that each partition can be represented by a special type of binary tree, and we call that a canonical tree. The characterizing feature is that the vertex degrees are non-decreasing on each level. So basically, here we're only allowing degrees 0 and 2. So you have all the leaves on the left, and then all the vertices of degree 2 as far right as they possibly can. Here I'm showing as an example the partitions of length 5 powers of 2 that add up to 1, and the associated canonical trees. And just looking at these examples, I think it's reasonably intuitive what is happening here. The leaves, more specifically the depths of the leaves, encode the exponents. And to see that any such canonical tree really corresponds to a partition of 1, so that these really add up to 1, can be seen by a simple induction. Because if you take a leaf and split it into 2, so you can think of taking this leaf and splitting it into 2, the associated fraction gets replaced by 2 fractions of half the size, so the total sum doesn't change. So in the example, we see that there are 5 possible partitions of length 5, and there are 5 canonical trees. Now, one might wonder how many there are in general. And to do that, one can use some generating function trickery. It's useful for that purpose to use an auxiliary variable that keeps track of the number of leaves. So if we write m for this quantity and n for the total number of internal vertices, and if we define a bivariate generating function associated with that, then we get a functional equation, as we'll soon see. Namely, we can argue as follows. So a canonical tree is either just a single vertex, which gets u associated with it. The single vertex is a leaf, not an internal vertex, so there are 0 internal vertices in that case, and there is 1 leaf at the last level, so that's this term u here. If it's not that, then I can obtain it from a tree of smaller height by splitting some of the leaves. Let me go back here. So this tree would be obtained from the smaller tree here by splitting the last leaf. This tree over here would be obtained from a smaller tree by splitting the last 2 leaves each into 1. This one would be obtained from the smaller tree here by splitting the last leaf. So I can get each tree by splitting sum of the leaves at the last level in a smaller tree, which is given here. So if I have a tree with m of t many leaves at the last level, then I can split between 1 and m of t many of them to get a larger tree. In this way, if the number of splits is j, then I'm creating 2j new leaves at the last level. I'm creating j new internal vertices. So that's the contribution I'm getting. And in this thing here is just a geometric series, which is very nice. So I can express this in terms of the generating function h. A slight drawback perhaps is that you don't get hxu, but rather you have something else here instead of u. What you can do, however, is you can iterate this. So basically you repeatedly plug it into itself. At the end, then you solve for h, that's possible. And then you plug in u equal to 1. And you get this expression for the generating function h. I can now forget about the number of leaves at the last level. I no longer really need it, so I plug in 1 here for u. This was an auxiliary quantity. And I'm getting an explicit expression for the generating function. The generating function looks admittedly quite ugly. So you have an infinite sum of something complicated. But it turns out that you can analyze it quite well. The smallest zero of the denominator determines the asymptotic behavior of the coefficients. And you find an asymptotic formula like this. The a and b here are certain constants. This was shown independently by several people in different contexts. So some were looking at trees, some were looking at code, some were looking at partitions. This occurs in several different papers. One thing that one notices perhaps is that there is a difference to the asymptotic formulas we got for simply generated trees, where there was an additional n to the minus 3/2. This is indicative of the fact that the generating function has a different type of singularity. It's not a square root singularity, it's a pole singularity that dominates. And not just that, if you study the structure of these canonical trees, which we did in a paper from 2015, if you study the structural properties of such canonical trees, just pick one of them at random, then you find that these look rather different from simply generated trees or other types of trees. So they're quite tall. It's one thing one can observe. So we found that the average height is linear in the number of internal vertices. So it's asymptotically equal to some constant times n. One can work out this constant. One can also work out the asymptotics of the variance, which is also of linear order, so asymptotically equal to some other constant times n. And the central limit theorem holds, which means if you subtract the mean and divide by the standard deviation, then you get convergence to a normal limiting distribution. What you get about canonical trees immediately also translates to the other combinatorial quantities or combinatorial objects that I showed you. For example, the height of the tree is simply, it corresponds to the highest exponent that you get in your partition of 1. So in a typical partition of 1 into n powers of 2, the largest exponent that occurs tends to be rather large, so linear in the numbering. We did not only study the height, also other types of quantities. For example, the trees are quite narrow or much more narrow than, for example, the simply generated trees. The width is only of the order of magnitude of logarithm n, as it turns out. All right, but let me move on to my second example. These are increasing trees with label repetitions. So I got involved in enumerating these recently. The question is quite simple, actually. I told you earlier that binary increasing trees are counted by the factorials. That's a very nice and simple counting formula. But how does this change if you allow repeated labels in your trees? So the labels still have to be increasing from the root to the leaves. And there cannot be any gaps in the set of leaves, but some of them can be repeated. So you can think of this as repeatedly attaching, but you're allowed to attach more than one at once. So you start with the root and you attach. And now I'm attaching 2 vertices labeled 3. attaching also 2 vertices, label 4. I can also attach more, so let's say 3 vertices, label 5. Or maybe just 1, label 6. And I'm getting something like this. So it's still binary. I can have left and right children. I have increasing paths from the root to the leaves, but labels can occur repeatedly. So of course, this increases the number somewhat, but it's not entirely obvious how. So what do you get instead of n factorial here? And again, generating functions can come to your rescue. So if we first look at the ordinary generating function, it actually satisfies a very nice functional equation. Namely, you've got this. So I consider binary increasing trees with n-1 vertices. This will be somehow helpful. n-1 vertices means that there are n external vertices, so n places where you can attach something new. Now, such a tree would either be a single internal vertex with 2 places where you can attach. That's the term x squared. If it's not that, then you get it from a smaller tree by attaching in a number of places. And at each place where you are allowed to attach, you either do it or not. If you do attach, you have to replace x by x squared, and because you're getting something new. If you keep a place where you're allowed to attach as it is, you just have the term x. By substituting x plus x squared into the generating function, I'm basically mimicking the process of substituting some of the places by either just keeping them as they are or letting a new vertex go there. And so I just subtract b of x, which is the scenario that I'm not attaching anything new. So every tree that I'm counting here is either the 1 vertex tree or it's obtained by some extension, which is given by this expression. I can, of course, write this equivalently like that. And this looks very nice and simple. But actually, as it is, it's somewhat useless because functional equation might be nice, but the generating function b is not very well behaved as an analytic object. The radius of convergence is 0. So what you have to do instead to count them is to actually translate the functional equation into a recursion after all. And then one can define an auxiliary sequence that gets rid of the convergence 0. The denominator here is not completely random, so there is a heuristic argument why you should take it exactly like this. Once you do that, based on this recursion, you can obtain a differential equation now for the generating function associated with this new sequence b. And while this differential equation might look less nice, it is actually not so bad. It's a linear differential equation. The auxiliary function a is a bit complicated, but as it turns out, we don't need to know so much about it. And because it's linear, one can solve it explicitly, at least in terms of integrals. And that is enough then to perform an asymptotic analysis. So I can infer analytic information about the generating function. And at the end, there is an asymptotic formula for Bn, little bn, and then because it's related to the capital Bn, the number of binary increasing trees with label repetitions in a simple way, one obtains an asymptotic formula for the capital Bn's, and this formula looks like this. So without the label repetitions, you would just have the factorial here, but now we're getting some additional factors, specifically this exponential term with the logarithm of 2. Something that's quite unusual is that you have the logarithm of 2 also in the exponent. This is a very strange behavior. Somehow you don't see this very often. As I showed you earlier, for example, for all the simply generated families, it was always 3/2, not ln 2. All right, so my last, okay, this also generalizes to d-ary trees. You get slightly different constants and exponents and so on, but sort of qualitatively, it's the same kind of analysis. All right, I have a few minutes left, I think, so I will present my last example. So this is an interesting case that leads to exact counting formulas that were somehow unexpected and surprising to us. So to explain how one gets there, one starts with the Catalan number. So this is the number of plane trees. And then it was shown that if you count all the independent sets in all the plane trees within vertices, the number is something that's sort of like a Catalan number. So it's a generalized Catalan number. This was proven in a paper by Kirchenhofer, Proding, and Tichy in 1986. And it looks the same up to sort of exchanging 1 and 2, 2 and 3. So what we were wondering then, somewhat later, was, well, does this generalize? Can we define something like this with 2 replaced by 3, replaced by 4, 5, 6, and so on? And one of the ways to do that is to interpret this as plane trees with colors. So you take 2 colors, let's say more than vermilion, and you impose that 2 adjacent vertices may not both be colored vermilion. So then the independent set is the vertices that are colored vermilion, because no 2 of them may be adjacent. And the remaining vertices that are not in your independent sets are the morph vertices. So you've got a different interpretation of this result, and this generalizes. So if you take plane trees and color them using k different colors, but with a certain restriction, then you get nice counting formulas. The restriction is that colors Ci and Cj are only allowed for adjacent vertices if I plus j is not too large, at most k plus 1. Now, if k is 2, you're getting exactly what I said earlier, because then everything is allowed except C2 and C2 being adjacent. Now, we call these k-plane trees, and we're able to show that the number of k-plane trees within vertices is precisely this. So exactly what we were dreaming of. And there are some bijective relations to other things counted by these numbers, some paths and other types of trees. But you can also obtain this by generating functions. And more recently, we got interested in looking at this in even greater detail. So here's an example of a 4-plane tree. You have vertices colored in 4 different colors, but I also included labels 1 up to 4 to illustrate this better. So you see that the sum along any edge cannot be more than 5. Now, one might wonder, is it possible to count such trees, including full information on how often the labels are used? So we would like to know how many might be like for 4 plane trees. If I prescribe how many vertices there are of each color, you get something like this. Now, this was quite surprising to us because you wouldn't necessarily expect such an explicit formula for something so specific. The way to get this is that, again, we're using our friends generating functions. You can encode the coloring condition like this. The denominator here goes only up to k plus 1 minus r. This encodes the fact that if your root has color CR, then the color of all the children can only be anything up to k plus 1 minus r. So you have this system of generating functions. Then you use a suitable substitution, which admittedly, if you look at it for the first time, is not intuitive. But if you have guessed the formula beforehand, then it's actually the most natural thing to do. And then it's really just an application of the Lagrange inversion formula. Okay, and we thought that this was just a nice curiosity, somehow a weird, wonderful counting formula for some specific types of trees. But recently, these trees have appeared in a completely unexpected context related to random matrices. So when you study trees, it seems that you really never know. And these were just some examples of trees, families of trees, enumeration problems related to trees. I could talk for a lot longer, but I think my time is over. So I thank you all very much.